on the fingertips, their hands, okay? You think that was bad? If we did it on the back of his calf or on his back, we would have had him like, way far apart, and he would think that we're hitting the same spot. Okay, that's sort of what we mean when we talk about resolving ability in terms of being able to tell the difference between 2 points. You guys with me so far? All right. Well, this means we're limited to what we can magnify using visible light. Okay, Eric alluded to this already. Well, you mean that means that blue light would be better than red light? Yes, it would, because it has a shorter wavelength. But there comes a limit to which we would not be able to discern between 2 points, because if those 2 points are closer together than 400 nanometers, it's going to look the same. Of course, the solution to that would be to simply move to what? Ultraviolet and X-rays and gamma rays. We go to higher and higher frequencies. The problem is this: even though we have the technology for the device to look at an ultraviolet and then translate it into visible so we could see it, okay, we could do that. The problem is, as you go to higher and higher frequencies, that is shorter wavelengths, you also are dealing with more and more what? What? Energy, that's right, Joe. You're going to be dealing with more energy, and that energy could have so much energy it could actually damage what you're trying to actually go ahead and look at. You see the problem? But we can take advantage of the electron. The electron can behave as a wave. And here's the cool thing. It's not a form of EMR. So its wave, the electron doesn't carry the same damaging energy that higher frequency EMR would have associated with it. And the wavelength for electron is far smaller than that of something, say, like a smaller than that of visible light. Consequently, we can actually take advantage of it, and this is what's responsible for things like this. Let me show you a couple little pictures taken with electron microscope. There it is. Okay, there's one little guy. Take a look at this little guy, isn't it? Look at the detail. Look at that detail. This was taken using an electron microscope. This is a picture of a common midge or gnat. Anyone who's played center field knows what I'm talking about. Those little things that, that fly around. Yeah, that's this guy right here, okay? And you can just see the detail. There's no way you could get that with visible light. There's just no way you could get that amount of resolution. Now here's another picture. This picture was taken again, and what they did was they color enhanced it. What you're going to be looking at is a sewing needle. The sewing needle has been colored purple just so you could see what it looks like. And there's some little micro beasties at the bottom there. So the yellow that you see on the needle is bacteria. So you can see we've taken a picture of it. Yeah, and you can see the sewing needle at different resolutions and the bacteria on the sewing needle. And there's little micro beasties down here that are using this. Little micro beasties at the bottom. And again, you just do not get this. This is just a nice practical application of taking advantage of the wave-like nature of matter to get this kind of resolution. Now, I saw some of you looking at the little micro beasties I was pointing to at the bottom. Some of you I know might actually recognize these little guys. What are these little guys down here? What is it, Kyle? These are what dust mites are. These are dust mites. You see the little flakes right there? Okay, yeah, that's actually, you guys understand what dust is, right? 90% of dust is exfoliated skin, that's right. Yeah, and so this is actually skin cells, little pieces of skin tissue that have been exfoliated, sort of like taco chips from heaven as far as the dust mites are concerned. They just sit there and, gnash away and eat at them. Of course, dust mites, if they're going to get a steady supply of exfoliated skin, I mean, probably the best place to be would be where? Where you spend so much time. In your bed. So, yeah, in the room. Yeah, that's where these guys really like to hang out. Now, if you change your bed linens, you know, say once every week or once every 2 weeks, there's probably not that many in. Say maybe, I don't know, at most 20,000 or so. Now, if you don't change it but once a month, oh well, we're probably into the probably close to 1 million, maybe 2 million of these. Now, I know there's going to come a time when it's, you know, storming out, it's late at night, your parents went out for the night, and you're getting ready to go to bed, and you might be a little nervous. As you lay your head down on your pillow, don't be afraid. You're not alone. You have lots of little friends with you.
Yeah, I'm cool with that. Just breathe in.
Have you ever heard the expression, ignorance is bliss? Now you know why. Okay. I should point out, the dust mites, you don't have to fear them. They do not eat living tissue. They only eat the dead flakes of skin that are on you. I mention this because they do like to sometimes jump on you and graze. But if you're going to be a dust mite eating exfoliated skin, the best place to do is where you're exfoliating at the fastest rate. Of course, you know where that is, right?
Your hair.
No, your eyelashes. Right where your eyelashes connect with your eyelids. Now, if you took a shower, chances are you rinsed them off today. Yeah, so they're gone. But by the way, now some people happen to be allergic to dust mites. Pardon me? What?
How does that what they say when you're allergic to dust?
When no. Well, I mean, if you're allergic to dust can be made up of other things besides exfoliated skin. So it could be pollen or other things too. But yeah, it could be. But it could be the dust mites you might be allergic to. People who are allergic to dust mites technically not allergic to the dust mites themselves. You have to understand that while they're sitting there munching on the exfoliated skin, you know, eventually they have to go. They don't get up out of your bed to use the restroom. They basically go where they are, and so the fecal matter of the dust mites, it produces an allergic reaction in some people when it gets into mucous membranes like your eyes and your nose, and that's actually what they're allergic to. So some people happen to be allergic to the fecal matter of the dust mites, but most people are not, so don't have to worry about that part. Questions at all? Yes?
Okay, so wait, how do we take pictures of atoms that also, like, you know how...
We actually have taken, and if you come over here to my bulletin board, you'll see that the guy, apparently some of the ladies and gentlemen over at IBM Laboratories had a little bit of time on their hands. They were playing around with a scanning tunnel electron microscope, and because it carries a charge on the tip of it, they were able to actually reposition individual atoms. So what you're looking at are actually pictures of xenon atoms, and they positioned them to spell out the world's smallest sign, IBM. So they spelled out IBM using individual xenon atoms. These are actually atoms that you're seeing. So yeah, that type of resolution is what we're talking about. Questions at all? Okay, well, that really does carry with it then some interesting things, because that means now we have a new way of looking at things as far as with quantum theory and working out our world, and that gave rise to a new model of the atom, and I want to talk to you about that today. And this is Niels Bohr. Bohr had looked at the atom, the model of the atom that we had at the time. Remember how we could not explain why electrons didn't spiral into the nucleus, right? Okay. When he saw this, he said, well, look, you know, I'm looking at this work done by de Broglie, by Einstein and Planck, and he said, look, I think the reason why we don't see the electrons spiral into the nucleus is because at the atomic level, I think physics works differently. Okay, normally an orbiting satellite radiates energy, and so it loses energy and eventually will be pulled into, for instance, the gravitational pull of the Earth. That never happens to the electron. Why is that? Well, he said that I think it's because as long as you don't give the electron any extra energy, it won't release energy. And what he did was to base a model on the atom that was based on the first part of quantum theory. So his model is based on the first part, put forth by Planck and Einstein, specifically that EMR, or energy. Energy could be quantized. It could come in very specific amounts. And he assumed that the electron was quantized with respect to energy, that the electron could only have very specific amounts of energy, not just any old amount. He made this assumption and said the following: I think the atom looks like this. I think here's our nucleus. I think the atom consists of the fact that the electron is moving about any one of several fixed circular orbits. Now guys, take a look at this for a moment. If I erase it like this, and just show that much, can you imagine it?
Yeah.
Okay, you can imagine the rest of it. I'm going to do that because it's just going to be easier to draw to show you what I want you to see. He said that the electron moves in any one of these fixed circular orbits. Now, when I say orbit, that's a little bit of a misnomer because it's not a two-dimensional orbit. I'm sort of think of it this way. You imagine a basketball, right? Okay, if there was a BB inside of the basketball, if you move the basketball in the right way, you could get that BB running around all the inside track all the way around, right? Sort of like a shell. That's how he's looking at the atom. He's thinking the electron is moving in what is known as an electron shell, or we call it an orbit, but you could also refer to it as a shell. And so here's my nucleus, and the electron could be moving into this orbit. It could be moving in that orbit. Actually, let me draw this differently. There we go. It could be moving in this orbit or this orbit, and you'll notice that I'm purposefully drawing them in a particular way. He maintained that as you go further out, the energy associated with a particular orbit increases. You guys know what a record player is? Okay? If you put your finger around the record player near the center, your finger goes like this, right? If you put it on the outside, it goes a lot faster. The idea being the further away you are from the nucleus, the more energy the electron has associated with it. Fair enough? So I'm just going to make up numbers. These numbers are not real. I'm just going to make them up just for the sake of our discussion. Let's suppose that this first orbit has associated with it 100 units of energy. Because this orbit has a particular amount of energy associated with it, we can call that our first energy level. So E sub 1 represents what is called an energy level. We can refer to the orbit as an energy level. The second energy level would have more energy associated with it. We'll say it has, say, 300 units of energy. The third energy level, the third orbit, a little bit further out, has 350 and 375 for the fourth energy level, and so on. So as you go further out, the energy levels increase in energy, and the amount of energy they have decreases. In other words, in relation to one another. So that as you go further out, the energy levels get closer and closer together, and so they get closer together in terms of the amount of energy they possess as well. So far, so good? Maria?
Just read that last sentence again.
Yeah. So what he's saying is this. He assumed that the electron was quantized with respect to energy. The electrons could only have a certain amount of energy, and as long as you didn't give them any extra energy, they wouldn't give off any energy. The energy the electron has is dependent upon which orbit it happens to be in. There are several fixed orbits or shells or energy levels that the electron can reside in. And as you go further out, the amount of energy associated with that energy level increases. Okay, so further away from the nucleus, the energy levels have more energy. But as you go out, the energy levels also start to get closer and closer together. So this guy, the next guy would be right here. So they get progressively closer and closer together. Question so far? Now, this model, as I said, is based on the first part of quantum theory, put forth by Planck and Einstein, that energy could be quantized. Specifically, he's looking at that particle-like nature of energy. And he assumed that the electron was quantized with respect to energy, and he set out to try to make a model of the atom for hydrogen. He figured, let's do hydrogen first. It only has one electron, so it'll be simple. We can look at it. He said, here's what I think is going on. The electron, typically, we expect to find in this first energy level. Why is that? Well, it's the lowest in energy. What is the relationship between energy and stability? Yeah.